So let's look at Lewis structures. Lewis structures just basically try to show you where the electrons are distributed around atoms in a molecule. They're fairly straightforward once you get your head around them. So we're looking at a couple of things here, using dots to represent electrons. So we've got a lone pair of electrons there represented by two dots, and also this straight line connecting the two atoms together is a covalent bond. We look at something called the octet rule and then formal charges later. And the octet rule is just basically about stability associated with having 8 valence electrons, 8 outer electrons. And really it's only dealing with relatively small atoms. If you go into period 3, then the octet rule sort of starts to become less relevant. But we'll come to that later. So the first thing we need to look at are these Lewis structures. So there is a method that you follow. So let's have a look. So we've got hydroxide ion there, OH minus. You should be used to seeing that. So what we need to do is we need to add up valence electrons. Valence electrons are the outer shell electrons, or the electrons involved in bonding, and certainly for our level, just think of the outer shell electrons which in the atom as an element. So it's obviously referring to the group number 2. So we can think of valence shell electrons, outer shell electrons, and group number as all the same, and then we adjust for any charges. So when we adjust for charges, what it means is that if we've got a negative charge, we've got an additional electron, so we need to add 1 onto the total number that we're considering. So we'll explain in a minute. So let's get rid of these now. So if we look here at our example, we've got oxygen, which is in group 6, and there's only 1 of them, and we've got hydrogen, which is in group 1. So the valence electrons 6 and 1 is 7, but we've got this negative charge, so the negative charge is 1 extra electron, so that adds 1, so we get a total number of electrons of 8. You start off drawing the structure, so it's just a simple structure with a single bond between each atom. So there's only 2 atoms, so we just draw 1 bond. The next thing we need to do is put in any lone pairs. Now remember, we've only got 8 electrons to put in total. 2 of the electrons would have been accounted for in the bond, so we've only therefore got 6 electrons to put in. The first thing you need to make a note of is that with hydrogen, the formal charge is always going to be 0, because it's only going to ever have 1 bond. And there are no lone pairs of electrons because it's so small. So if you remember the structure of hydrogen, it's 1 and 1. It's just got 1 electron. That 1 electron is in the 1s. And the 1s can only accept 2. So as soon as you put a bond to hydrogen, the 1s2 is full. And that's it. So we know that we've got 2 electrons from our total of 8. 2 of them are in the bond, so we've got 6 to put in. They can only go around the oxygen 1, 2, 3, 4, 5, 6. And that's it. That's a simple Lewis structure. We wrap the square brackets around it and put the charge. So what we need to consider is what these formal charges actually mean. So if the formal charge is the charge on the individual atom within the molecule or the ion, the molecular ion, here it's called a polyatomic ion. So lots of words, but basically you should be able to work your way through. So we're going to find out why the oxygen has a 1- formal charge and why the hydrogen has a charge of 0. Again, there's a little sort of routine that you have to get into. Once you crack the routine of drawing Lewis structures, everything could be clear. This is what we're going to use. The formal charge is the number of valence electrons on the atom, so the group number, the number of unbonded electrons, so lone pairs usually, and the number of bonding electrons divided by 2. You'll see this in books. This is why I've included that there's an easier way to come up with a formal charge. Okay, so we'll stick with the hydroxide. We're going to see how we actually calculate the formal charge for each individual atom. So we draw the Lewis structure. We've seen that before. We know that in the Lewis structure we've got two covalent bonds, two electrons in the covalent bond, and we've got 1, 2, 3 lone pairs around the oxygen. So we need to count up valence electrons for each atom and the number of unbonded electrons, and then we need to consider the bonding electrons divided by 2. Really, you should just be looking at the number of bonds attached to it. It just makes it easier. So for oxygen, we've got a group number of 6, so that's 6 valence electrons. The unbonded electrons, 1, 2, 3, 4, 5, 6 unbonded electrons. So we've got 6 minus 6. And then it's the number of bonded electrons divided by 2. Or, as I said before, you can just think of the number of bonds. So we've got 6 for the group number, minus 6 electrons unbonded, which are those, minus the 1 bond. So 6 minus 6 minus 1 gives us a minus 1 charge. For hydrogen, I've already mentioned that hydrogen, the formal charge is always going to be 0 because we've got a group of 1 for hydrogen. So group 1, so 1 valence electron, minus 0 unbonded electrons. There's no dots that you can see around that, minus the 1 bond. So the bonding electrons, there's 2 bonding electrons in that covalent bond, divided by 2 divided by 2 is 1. So we end up with 1 minus 0 minus 1 equals 0. It's always going to be 0 for the hydrogen in our examples. Again, wrap the square brackets around it to put the charge on, because the charge is generated, or the charge is calculated, sorry, from the minus 1 plus the 0. So let's have a look at an example. We're going to try and construct the Lewis structure for ammonia. So we've got NH3, so the central atom is the nitrogen, and we've got 3 hydrogens attached. So there's our skeletal formula. So just single bonds. So we go up to our calculation here. For nitrogen, number of valence electrons is 5. For hydrogen, we've got group 1, but we've got 3 hydrogens, so it's 3 times 1 is 3. There's no charge, so we don't include the charge. So 5 plus 3 is 8, and that means we've got 8 electrons to put in. But we've already got 2 electrons there, 2 electrons there, and 2 electrons in the bond. So out of our 8 electrons, we've got 6 already in total. The only place we can put these, the final 2 electrons, they're going to be unbonded. It's going to be a lone pair on the nitrogen. You should recognize that from your work on shapes of molecules. So when we try to calculate the formal charge on each atom, we go through the same process. So for nitrogen, nitrogen is group 5. So 5 valence electrons, 2 unbonded electrons, 3 bonds, 1, 2, 3. So 5 minus 2 minus 3 gives us 0. There is an easier way to look at it, and I've actually included it in the presentation. If you have a look where I've drawn this ring around the nitrogen, if you just count up everything in the nitrogen, sort of literally what can you see? We've got 1 electron, another electron, 1 bond, another bond, and another bond. So we've actually got 1, 2, 3, 4, 5 things in. So we take the group number minus everything in the ring. So 5 minus 5 is 0, obviously. Everything in the ring literally means any electrons and any bonds. Okay, so let's say we can consider the hydrogen. All the hydrogens are equivalent, they're all exactly the same. So we've got, for hydrogen, group 1 minus, there's just one bond, so 1 minus 1 is 0. So that's why we get 0 all the way down here in the table. So we end up with a formal charge for the whole of the molecule of 0, because it's 0 added to 0 added to 0 added to 0, 0. Okay, we're going to look at the ammonium ion, NH4 plus. You should be familiar with the ammonium ion. It's formed when ammonia forms a dative covalent bond, a coordinate bond with a proton. And you should remember this from the shapes of molecules work 2 in year 1. So anyway, we've put the skeletal structure in. So we've got nitrogen surrounded by 4 hydrogen atoms. So we've got the nitrogen in group 5, so 5 valence electrons. We've got 4 lots of hydrogen, hydrogen group 1, so 4 times 1 is 4, so we add them together, we get 9. We take 1 off for the charge because we've got a positive charge. So if we add 1 for every negative charge, we need to take 1 off for every positive charge. So we've got 1 positive charge, so we take 1 off. So 5 plus 4 is 9, minus 1 is 8. So that means we've got 8 electrons to put in. Well, we've got 2, 2, 2, 2. So every covalent bond is 2 electrons. So basically, drawing that out, we've accounted for all of the electrons in the covalent bonds, and we don't have any lone pairs. However, we still need to go on and calculate the formal charges. It's the same process. Go with the idea of drawing a circle around each atom. So what we can see there, we can see the nitrogen, and we've got 4 things within the circle, 4 covalent bonds. So if we've got group 5 for nitrogen, no unbonded electrons, minus the 4 things in the ring. So it's basically just group 4 minus group 5, actually, isn't it? Group 5 minus the 4 things in the ring that we've drawn around the nitrogen. 5 minus 4 is 1, so that gives us the 1 there. And we do the same, but we know we've got hydrogens bonded all around, and we know that hydrogen's always going to be 0 because we've got group 1 minus 1. So we end up with an overall formal charge of the 1 plus 0 plus 0 plus 0 plus 0, so that just gives us 1. So we end up wrapping our molecular ion in square brackets and putting the charge on the outside. You're getting used to the format now. You should becoming familiar with this. We'll look at the nitrate ion, NO3. It's a little bit more sort of tricky here because we need to consider the Lewis structure in more detail. Okay, so let's have a look. We've put in the nitrogen as the central atom, and we've got 3 oxygens attached to that, so everything looks fine there. However, we've got NO3 minus, so we've got 1 nitrogen of 5, 3 lots of oxygen, so 3 lots of 6, so that's 18. We've got 1 minus charge, so we need to add a 1 onto it. So by the time we've got 5 and 18 and 1 gives us 24. So we've got 24 electrons to put around the atoms in that molecule. But we've already put 2, 2, 2 in there. So we've already put 6 in. So we've got 18 electrons to put in total. So they should be shared. The first thing to do is attempt to put them around the terminal atoms. So the atoms that aren't the central atom, you put them around the things that are bonded to the central atom. So we'll put our lone pairs in. So there we go. Now what we hit now is that we've got a bit of a snag, that we've got the nitrogen doesn't conform to the octet rule. The octet rule means that we need to try and get 8 around that central atom. We've only got 6 at the moment. So the octet rule meaning that we have increased stability if we can get 8 electrons, 8 valence electrons around an atom. So we've only got 6 at the moment. So basically we would borrow a lone pair of electrons and form a double bond. That will ultimately reduce the charge, the formal charge on the nitrogen. So basically what we have here is if we throw a ring around the nitrogen, we get group 5 minus the 1, 2, 3, 4 in the ring. So we've got group 5 minus 4 equals 1. There we go. And then let's have a look at the oxygens. Now the oxygens, we've got 2 sorts of forms of the oxygen. We'll look at the first one with this double bond. So we've got group 6 for the oxygen, minus 4 unbonded electrons, that's a 2 lone pairs, and then minus the 1, 2. So 6 minus 4 minus 2 equals 0, so that's why we come out with a 0 there. The other 2 oxygens, they're identical, but they're different to this first oxygen. So let's have a quick look. Here we're still in group 6, but we minus 1, 2, 3, 6 unbonded electrons, the 6 electrons that make up the 3 lone pairs, minus the 1 bond. So they end up with 6 minus 7, which is minus 1. So that's why these 2 are minus 1. What that means is that when we total everything up, that we get 1 plus 0 is 1, plus minus 1 plus minus 1. So we end up with an overall charge of minus 1. Wrap the square brackets around, and then that's done. Now we come to the final example, the sulfate ion SO4 2-. You should recognize SO4 2- from your work on acids at GCSE, and possibly work on hydration of alkenes to produce alcohols in year 1. Anyway, we're going to look at this sulfate ion. We've got sulfur in the middle, so that's our central atom. The reason it's a central atom, it's bigger. It's in period 3, so it can basically we can start to put more electrons in. So it doesn't necessarily adhere to the octet rule strictly. It's because we can get more than 8 electrons in our outer shell for sulfur because it's a bigger atom. Anyway, it's in group 6, so it's got 6 of its own valence electrons. Oxygen is in group 6 too, and we've got 4 of them, so we've got 6 plus 4 lots of 6, which are 24, so that brings us up to 30. And then we've got 2 extra electrons for the 2- charge, so that means we've got a total of 32 electrons to put in. We've already got 2, 4, 6, 8 electrons for those covalent bonds bonding the sulfur to the oxygen, so we've already got 8 electrons. So the remaining electrons need to go in, and they need to be shared equally among the remaining atoms, so we can put them in. So we've got let's see, 6, 12, 24 electrons to put in. So let's have a quick look. So we would then throw our ring around the sulfur. So we've got our sulfur, which is in group 6. They're all in group 6. So 6 minus 1, 2, 3, 4 equals 2. So that's why we come out with 2. And then all the oxygens are equivalent. They are 6 for group 6, so 6 valence electrons minus the 4 unbonded electrons minus the 1 covalent bond that you can see within that circle that we've drawn. So we've got 6 minus 1, which gives us minus 1 in total. So for this version or form of the sulfate ion, we come out with an overall 2 minus charge, because we've got 2 plus 4 minuses, which we come out with 2 minus overall. But there's something that we need to consider. We made reference to this before, that when we're drawing a Lewis structure, we need to try and reduce the formal charge on each of the atoms that we've got in the molecule or in the ion. So basically we need to revisit this. There's a way in which we can reduce the formal charge on the sulfur. That's a little high. Now, we've already explained that sulfur can accommodate more electrons. So we've only got 8 electrons in it at the moment. We can actually throw a couple more in, and if we put more electrons in, we can reduce that formal charge, which is basically what we're looking for. So the way we do it is we think about taking a lone pair off one of the oxygens and forming a double bond, and doing exactly the same with another oxygen. So we've still got the same number of electrons. We've just removed a lone pair from 2 of the oxygens and put them into the sulfur and formed a double bond. But when we do our calculations, what we will see is this sulfur now in group 6 has got 6 things within its ring. So it's got 1, 2, 3, 4, 5, 6 covalent bonds. So that's 6 minus 6 will give us 0. So that's reduced the formal charge on the sulfur. Let's say these 2 oxygens, they have got a formal charge of 0 too, because we've slightly altered them by putting the lone pair into bonding pairs. So we've actually been able to make that formal charge 0, which is a little bit better for us. And then these 2 oxygens, they're the same as the oxygens that we saw initially. We haven't done anything with them. What that means, the upshot of that is that we come out with a more favourable structure for our sulfate ion. It's still got a 2 minus charge, because we've got 0 plus 0 plus 0 plus 1 minus plus 1 minus, which gives us 2 minus overall. But it's because we've got significantly these 3 formal charges are reduced to 0. That's better.